Welcome everybody, it's SREcon, it's day 3. I am the only thing standing between you and lunch. So let's get going, shall we? Yes, this is Financial Resiliency Engineering. It is not a pitch for a new discipline or a new conference. There will be no FREcon, at least not organized by me. I'm going to talk to you today about some work Shopify's done over the last little while to get a better handle on our cloud infrastructure costs, how we've brought them down, and how we're going to keep a grip on them, hopefully, going forward. Quick intro about me. I'm Darren. I'm doing sysadmin type work for 20 years at this point, from computers under desks to computers in racks to computers in other people's racks now. I've been working at Shopify for over 6 years at this point on the production engineering team, working on Shopify's infrastructure. For those of you who don't know Shopify, it's a commerce platform. Our systems exist so that buyers can browse merchant storefronts, place orders, complete checkouts, and so that we can be the back end for our merchants' businesses, all the fulfillment and inventory and marketing, all that stuff. That's why our infrastructure and Shopify's application exists. Why this talk? SRE gets involved a lot with the non-functional requirements of our applications and our systems. The availability, performance, security, and efficiency is on that list too, but maybe we don't talk about it in terms of cost efficiency. And like the others, if we don't get this right, if we don't operate sustainably when it comes to how we the cost and efficiency of our infrastructure, we will eventually fail to meet our business objectives. Maybe not on the same time frame of an hour or half a day, but eventually, we won't be able to achieve our objectives if we can't get this right. A quick primer about Shopify's tech stack. It's a Ruby shop, mostly. We have a Ruby monolith at the core of our application. It's got lots of important infrastructure components. It depends on upstream and downstream, HTTP routers, load balancers, relational databases, streaming, caching, proxies for those things, connection multiplexers, all that good stuff. But we have several large applications we care about, not just the monolith. We tier 1 applications, we call them, each with their own upstream and downstream dependencies. And then a long tail, hundreds of smaller services, some of them facing our users, some of them just internal tools. We run all that mostly on Kubernetes on Google Cloud. But we run hundreds of clusters at this point, distributed all around the world. And so the detail I'll talk about in this talk will apply to this stack, but I hope that any of the principles will apply to any org, any stack, and will be useful and applicable to you. Just a quick primer on how our efficiency efforts looked in the longer past. Corey Quinn, cloud economics celebrity you might have heard of, has talked about this process looking like a sawtooth when it comes to managing your cloud costs, right? Slow increases and then sort of sharp decreases as attention and effort is brought to reduce the bill. And that this is to be expected. Yeah. The cloud is the utility, the flexibility is the point. We shouldn't expect predictable straight lines. But if we're being honest, I think our efforts before this point, and maybe you all see yourselves in this a little bit, these efforts were not very consistent. They weren't very plain tooth saw pattern. Some of these are the more exotic ones are a bit closer. Depending on the priorities at the time, how the prioritizing how much we were spending on our infrastructure and our services had lower or higher priority, depending on what was going on at the time. So a little story time. Sometime in the middle of last year, we get an alarm call from our leadership. Cost savings are really a priority at the moment. There's a sense that we're not getting good value for the money we're spending on our cloud infrastructure. And so, fine, message heard loud and clear. How do we get started? Loud and clear messages from very senior leadership brings people to the table. And this is an opportunity that we want to maximize and we want to seize. We set a target in absolute dollar terms. We want to bring our monthly spend down to between X and Y. This is a meaningful reduction, that we could rally an effort around, not 2 to 5%. And now, elephant in the room a little bit, I'm not going to talk about what those values were in absolute terms, partly because companies talking about their finances as a whole thing, especially for public companies. But also, I don't want anybody to think, oh, we should do exactly this, right? Your mileage may vary in your own context, but the thing to highlight is that it was not a trivial amount. It was an ambitious objective to set the expectation that we wanted people to really look at what could be done. There was a bit of concern, one of the risks potentially of this approach was that people cut too far, cut too deep, or cut in the wrong places, and you start pushing those resiliency or performance boundaries. But we have our SLIs and SLOs that can score us how well we're doing on that front, and so we feel that we can push the envelope a little bit and see what could be achieved. So we know we need to prioritize the work that's actually going to deliver what we need. We don't want teams of engineers spending days or weeks to save $50 a day. That's not a good use of anybody's time, and it's not going to help us achieve anything either. But we want, while we've got all this attention, we want to make the most of it and capitalize on all those eyeballs. So in the great traditions of ad hoc projects, it was time to make a spreadsheet. Now, we cast a wide net for ideas across all of the infrastructure and engineering teams, but with a strict time box of, say, a week, right? Write down everything you've already started doing. You've all heard the messages, so we can track what's going on. Or anything we could do quickly in the near future, maybe with a bit of priority shifting. And we very quickly got a lot of ideas on this list. I don't know if anybody heard Lauren's talk yesterday about not having the time to reflect and kind of step back. This was almost like giving people permission to reflect, and teams knew where the low-hanging fruit was instinctively, and they were ready and willing to go and tackle it. Give us an effort size just in T-set strategies, small, a day or two, medium, a week, maybe two, large, 2 to a month, XL beyond that, and also give us your best estimate of what this will save us in a month. And there was a few more bits on this spreadsheet, a particular GCP project for us, linked to a tracking issue, some more notes, maybe an owner field, things like that. But these are the key things we wanted to capture. So we take this short period to aim, and we tell people to pick the best options from the list and go and do the things. And so things started happening, and it was actually quite chaotic. I'm sure that was somewhat intentional from our leaders. They wanted to shake the tree and see what happened. There was a real buzz about this work. As I say, for the certain type of engineer, optimization work is great for them, and they were really ready to step up, really eager to get involved and to show what could be done. And so 1 week goes by, 2 weeks go by, 3 weeks go by. Those small and medium-sized bits of work start to land. But the impact on the daily spend was not quite as expected. Now we knew that not everybody, we wouldn't guess necessarily, engineers wouldn't guess all those things, right? You think that this experiment's finished and it's not, or that this infrastructure's not in use and it still is. So some work couldn't go as far, and we expected a bit of that, but more than we weren't getting the impact we expected early on. And we dug a little bit into this and found that teams were lacking the context they need to estimate the savings part. Teams are pretty good at estimating the effort sizes, it turned out, but the expected impact in dollar terms that teams and individuals had did not match the actual impact once that work was delivered. Missing, the context teams are missing was like what the real costs of things were. Shopify has things like negotiated discounts with Google, and also committed use discounts. I think it's savings plans in AWS, that not every engineer is going to have in their head at any one moment, and so they go to the pricing calculator and see the gross costs and things like this, and that's not actually what it costs us to run these things. So they didn't have that context that they needed to make that better judgment. And so we thought, can we give engineers tools to help with this? A quick handbrake turn into flame graphs, and let's define that as the collective noun for tools that lets us look at our tracing data, hierarchical tracing data, letting us explore it visually and try to understand them. Now, these typically work by serializing the tracing data into some intermediate format. This is a folded stack. Every line is a stack trace with a function separated by semicolons, and then there's a space, and then a unit, might be a count, for example. And then various tools can read these intermediate formats and let you visualize them. The one at the top there is the flamegraph.pl script from Brendan Gregg. The one at the bottom there is SpeedScope, great app for looking at your trace data. And that, that trivial folded stack example from before, we can see that function C gets called a lot, for example. So that might be a good place to optimize. For this audience, this will be no surprise. This is a more typical flame graph, a request profile of one of our open source applications. It allows us to kind of see at a glance, are we spending our time in the areas we expect, or are we surprised by anything? Can we do anything to optimize this? So profiling tools, flame graphs, are very useful for looking at hierarchical data, helping us find slow or expensive operations. Someone on our team had the inspired idea to see if we could turn our existing tracing tools to our billing data. We figured out how we could export a view of our billing data and our service data into these intermediate formats, and then turned our profiling tools to them. And it worked really well. So this example here is completely fabricated. It is the fever dream of a random number generator. The names and numbers mean nothing. But the same tools we can kind of see, particularly on the SpeedScope one at the bottom, that the Brother Spray project is very large, and then Compute Engine is the biggest part of that, and then GPU is the biggest part of that. So you can see at a glance where things are literally expensive. This is the same data, but in pprof format. Pprof is a format and a tool in the Go ecosystem for looking at profiling data. And again, the numbers are fabricated. Please don't pay attention to them. But we can see that Compute Engine is more than half the bill, and zoom in a little bit and see that GPU is a big part of that, and which projects contribute to it. This turned out to be a really great find. Engineers were able to use the tools they were already familiar with to get the context they needed on the real cost of things. So we did another pass of the spreadsheet, but giving engineers these tools so they could understand the real cost of things. We said to teams, take these tools, reprioritize, give us a little checkbox of the thing you're going to work on next with this new context. And we also worked with our NGOps and FinOps folks to revise the savings estimate essentially, just to make sure that, that what the engineers expected matched reality. And we had another big round of comms and a big push to say, okay, now everybody, new sprint, focus on the items that have been prioritized on this list and go. And this was much more successful in bending that spend curve. We, given engineers that missing context, taking a little bit longer to aim, found the right opportunities for us to bend that spend curve down. And in general, those kind of two areas for where we found our biggest savings. Incremental wins in our largest systems, where incremental wins are themselves quite significant in their own right. And for us, on our core application, we knocked up enough incremental wins that we could decommission, I think it was 2 whole clusters per region of that application, and every cluster has a fixed cost, so that turned out to be a really big win in the end. But also just turning off underutilized things, which you can find very easily centrally, or at least we could. We could see that this cluster, this application doesn't seem to be doing a lot. But you need to find the right people to give you the context, or that have the context to kind of go, oh yeah, that is an experiment, it could be turned off. You can't find that centrally very easily. And I want to go a little bit deeper and more technical on some of our biggest wins. Now this is probably going to be quite specific to our org, but I think a lot of you might find this interesting, and who knows, maybe some of these things will apply to your environments. The first one was the bin packing problem. Extreme tetrising. You have a number of things of varying size, and we need to efficiently pack them into a finite number of bins of fixed size. And for us, that is packing Kubernetes pods onto Kubernetes nodes, compute nodes. How well this is done had a big impact, or not done, not well it's done, had a big impact on our cost efficiency, it turned out. We improved this in 3 ways. The first one is not terribly interesting to talk about. GKE, Google's managed Kubernetes service, has a cluster autoscaler component, and the cluster autoscaler has a couple of different profiles and methods of which it can work. One of them called optimize utilization. It does this by, it's a bit of a black box, but we can define how it works, or we think we have. It works by making a tweak to the pod scheduler so that when new pods are to be scheduled, it will prefer to schedule a new pod to maximize the utilization of an existing node, rather than spreading the load evenly between all the nodes that already exist in the pool. And the second part of that is it will more aggressively evict pods so that they can be rescheduled on other nodes to increase their utilization. Obvious trade-offs of that are you will see more, if you turn that on, you will see more pod churning, so check your pod disruption budgets if you haven't. You will see high utilization, it does work, and that might surprise some workloads. Workloads that maybe didn't have high enough resource requests or resource limits, but didn't know because the average utilization across the cluster before kind of masked that. And be very careful using that with stateful workloads, stateful sets. The two I'm going to go a little deeper on are reducing the unallocated resources in the cluster. That's CPU and memory, which is on a node, but which has not been requested by any workload. And then right-sizing the actual resource requests on the workloads themselves. Now, this is a contrived example, but imagine we have a cluster, and the nodes in that cluster have 20 CPUs allocatable, and we have a workload that requests 8. So this means that at most 2 replicas could be scheduled on a node in that cluster. Now, if we scheduled if we wanted 100 replicas of that application, we would need to provision, excuse me, pardon me. Try again. So if we need 100 replicas, we need 50 nodes, which would lead to 200 CPU cores wasted, unallocatable in that setup. If we increase the resource request to 10, then 50 nodes would be enough for 50 replicas. But if we went even a little bit further at 10.1, then we could only schedule 1 replica per node of this particular workload. And for 100 replicas, we would need 100 nodes, but only with a fraction over half of those CPUs requested and allocated. That small change in this fictional example, had a very disproportionate impact on the overall cost footprint of this cluster. And no autoscaler strategy can help with this. This is as good as it can get. This is how that looked when visualizing it using our profiling tools. This is a real example, not compared to the fabricated ones from earlier. You can see it goes a little deeper. We actually have the project, the service, the SKU, a particular cluster, then applications in that cluster. That's usually organized by namespace, but there's some asterisks. And then the actual workloads within those, the Kubernetes deployments, for example. We started attributing CPU cores which were not allocated to anything to a virtual workload called kube unallocated. And we were able to sort of group this view at sort of higher levels. And the kube unallocated workload turned out to be one of our biggest applications when sort of counted as an application in its own right, just sort of summing up all the unused capacity across all the clusters. And visualizing it like this helped us very quickly find the setups and workloads where we had more work to do, where the greatest opportunities were. So how do we fix this? Well, first things first is how do we tell if workloads are requesting the correct amount of resources in the first place? Which brings us to the second item on that list, which is right-sizing resource requests. And a great tool to help with this is the vertical pod autoscaler. It's the horizontal pods autoscaler's lesser-known cousin. Its goal is to free users from the necessity of setting up-to-date resource limits and requests for the containers in their pods. And that's a very real problem. Resource requests bit rot very quickly. When your application is first deployed, you kind of make a guess about what you need, and then if it works, maybe you never look at it again. And even in an environment where Shopify, we are constantly deploying new revisions of our applications. We're adding new features, changing behaviors. Demand is going up and down. The odds at any one time that a set of resource requests and limits are reasonable and accurate is low. It drops depending on how much time has passed since the last time they were revised. And the VPA wants to help with this. It's made up of a few different components. Not going to talk about the second too much. They are the updater and the emission plugin. They're very much handled with care tools. The vertical pod autoscaler can proactively resize workloads on your clusters on your behalf, and it's those two components that make that possible. Before all this started, we actually already deployed the recommender everywhere to give us data about what this tool suggests our workloads should be using rather than what they're configured to use. The recommender works by, it's a controller. You deploy a custom resource which tells the controller to begin monitoring a particular workload, typically a Kubernetes deployment. And then it will start recording, it will start monitoring the actual resource usage of a workload and periodically update the resource itself with recommendations as to what resources it should be requesting based on its observed behavior, which is the target figure there. The lower bound, the uncapped target, and the upper bound are used by the other components in the VPA, which we're not going to talk about today. But the target is this controller's suggestion of what this particular workload should be requesting. We built some tools to scrape that value and put it into our monitoring systems. So we could overlay it with the current resource requests and limits, the current actual observed usage of it as well, so you can plot it. That usage aggregation is max, because you care about the peaks then you have to, making sure you can service your peak demand is an important consideration when setting resource requests and limits. Anywhere where there is a big gap between the current resource requests, which is the red line there, and the VPA's recommended resource requests is an opportunity for workloads to be downsized and to free up some more resource. I will say, if you do, in this specific case, the recommender's polling loop, the sort of resolution might be lower than your existing monitoring tools. So the VPA might miss very high sudden peaks of usage. So worth double checking using a tool like this, that the recommendation is a sane one, which in this case it seems to be. We've also built some tools to, so we had this data already in our monitoring systems based on collecting it from our clusters. And we have other tools to notify owners when there is a big gap between those two things and to automatically apply the recommendations, open the pull request automatically to their workloads, to apply the recommended value if they think it's a sane one. And just going back to this view for a second, you have to consider the size of your workloads and the size of the nodes together. The most perfect resource requests for any particular workload, like the 10.1 example here, might make it much harder for you to effectively bin pack your workloads onto your cluster nodes. Depending on your mileage may vary, more smaller pods or fewer larger ones might make it easier for you to pack all your workloads efficiently onto your clusters to minimize the resources you cannot allocate. It may even make sense in some way in your environment to have a fixed number of predictable pod sizes, a small, medium, and large pod configuration to make it easier to reason about and pick your node sizes. Or in the case of GCP, you can pick custom node sizes outright. If you already have standard pod sizes and you realize just by chance, your workloads all are similarly sized, maybe deploying custom node sizes will help you reduce those the number of unallocated resources. This is kind of local versus global maxima optimization stuff at the end of when you get down to it. But the thing to keep in mind is that the costs are a function of the size and the number of the nodes, not the size and the number of the pods at the end of the day. The third common pattern we found and when we had was around cargo culting. Anybody copy and pasted Terraform before? Yeah, I know I have. Engineers at Shopify have a great deal of freedom to build the infrastructure they need to solve the problems they have. And that's by design. We want people to be able to do whatever they need to do to solve the problems they have. We don't want to get in the way when they do so. But some examples we found through Terraform copy and pasting, clusters or workloads using faster or more expensive SSDs than was necessary for that particular workload, inappropriate or missing lifecycle policies on buckets, and more expensive machine types. Like I said, they'll copy from a workload that has a particularly high-performing CPU type that's appropriate for a workload, and it's just completely not appropriate for the workload they're doing. So we want to put guardrails into this process, but not outright set hard rules about what people can and cannot do with Terraform when building their infrastructure. At Shopify, we use Atlantis, which is a great tool for orchestrating Terraform on GitHub or GitLab pull requests. It integrates with a tool called Conftest for policy checking. You can write policies. Conftest lets you write policies against any structured data source, really, but in this case, against Terraform plans to make assertions against the data within that and to either approve or deny based on the kind of data within. This example here is somebody tried to create a resource with an N2D machine type, but it only thinks N1 or N2 are valid for this particular workload, for example. Anybody can dismiss these policy failures at Shopify. They're not hard gates. They're just there. They're a mechanism for us to inject into the critical path context that people might be missing. But if an engineer knows they know better, they are free to dismiss it and carry on. But more often than not, they're just informed about something they didn't know about in the past. And we can audit, we can audit the failures or the policy violations after the fact, because the violations will bit rot themselves. The policies we've written, the assumptions that are in the policies will bit rot over time, and we can use the frequency that people are hitting these things to review whether the policies need to be changed. And the policies are version controlled, so we have all the history as to why they were added and why they were changed and by who and when. So that worked very well. All right, taking a little step back about what we did and trying to think about the lessons we can draw. We were in a bad place, and we know that because we were able to significantly reduce our bill without having an impact on our users and our customers. That's not a good place to be. We don't want to slip back to that place, but we can't keep operating in the model of everybody stop what you're doing and help us save X, Y, Z, right? That's sooner or later we will cut where we shouldn't if we keep doing that. And it's not great for teams either. We don't want to keep getting in the way of people's roadmaps and interrupting them. So this stuff is the present and the work in progress for us. My selfish interest in sharing it with you all is if anybody has opinions about what good looks like, I'd love to have a conversation with you. And another confession, when writing this talk, my first draft was incredibly long. Turns out my colleagues are better at estimating than I am. So a lot of stuff has been cut out of this talk. If this section feels a bit truncated, it's because it is. So what might good look like? No surprises is kind of a theme for us. And if you don't want to be surprised about something, we need to have expectations ahead of time about what that thing should look like or be. So we're investing in tools to help us manage our demand, do traffic forecasts. Well, we have traffic forecasts. We do that regularly enough, but at Shopify, they're very much driven by our peak demand. That our flash sales at Shopify are a big thing. Black Friday is a big thing. Making sure that we have enough capacity to reach that peak demand and doing scale tests to make sure that we can has driven a lot of our infrastructure planning up until this point. Now we're doing more traffic forecasts more often on more dimensions, so not just the peaks, but also the baselines, the steady states, what's the minimum we expect, doing it on a regional dimension too. We can take, with these forecasts, are our autoscalers configured correctly? Can we actually do some scale tests and reach the peak demands we expect? Things like this. Capacity planning. So we can take those traffic forecasts and turn them into resource forecasts. How much compute do we expect to use to service this demand we are expecting? And then can we? If we're confident in our steady states, we should go to our cloud provider, make sure we've got those covered with committed use discounts, breakdown per region. Do we have the reservations we need to get that resource in the location where we need it? And better consumption insights, attributing workloads to who owns it and who's using it, how utilized it is, and things like anomaly detection as well. Is something more or less utilized than we expect it to be. And I want to drill down a little bit more into attribution. This was a big learning for us at the start of this project. We have to be able to get understanding and insights into the state of our infrastructure, the shape it's in, who's using it and what for. We had to build reports and build insights across several different data sets. And at the start of this process, we could do subsets of it. but not very easily, and it hindered our ability to find the right opportunities quickly. So here's 4 examples of data sets and the data that's within them. We had more, but the billing data is where the dollars are, what compute hours, measured in compute hours and memory hours, etc. An inventory of the compute things for which that billing is for, grouped into nodes or pods or buckets or computers, or virtual machines, whatever. The services that are running on that inventory, we think about the tier, how important it is, who owns it, what's its name. And then the teams responsible for the services. What org are they a part of? Where do we find them? How do we contact them? Now, joining across many different data sets, is, particularly doing that quickly, is very difficult. And so very quickly, things devolve back to spreadsheets. Someone will take a dump of something into one sheet, another sheet, and then pivot table this and pivot table that. And that's not sustainable or scalable either. We spent a lot of time this year trying to collapse our data to look more like this, to make our inventory more self-describing about all these other dimensions that we care about. On GCP, AWS, resources can have labels. In Kubernetes, resources can have labels. We spent some time to come up with a schema that works across our different systems. All these different systems have different limitations on character sets, character lengths, key values, things like this. But the more we are able to put context directly onto the resources themselves, the fewer systems we have to tie together to get insights about them. So the inventory now self-describes what tier it is, who owns it, who to attribute the cost to, because that's not always the team that's owning it, for example. COGS and OPEX are accounting terms. Everybody knows those, cost of goods sold and OPEX. A question we have is how much of our infra spend is COGS versus OPEX, and you don't want to have to build another system for that to track what service is COGS, what service is OPEX, or what cluster. Making the resources describe themselves gives you a lot more flexibility to report on this easily. And also consider things like compliance information. Is this resource in scope for PCI or GDPR or whatever? Self-describing resources have greatly reduced the difficulty level for us to understand our infrastructure on all these different dimensions. We haven't got to double key information across different systems and keep them in sync. It did take some planning to get the schema of that right, to find the lowest common denominator between the systems to apply the same label schema across all of them. But it's a real foundation for, it turns out we run many different multi-tenant systems. Some of them are on someone else's multi-tenant systems, on GCP, on Kubernetes. Some of them we built ourselves. Our internal services are used by many other teams. Who's using what part of it? Coming up with a consistent implementation schema to attribute, for resources to describe what they are, who's using them, what they're for, really has leveled up our ability to understand and report on what our infrastructure is doing. And the other thing we are talking more about now is in terms of unit costs. Dollars are one side of an equation. Right? There are numerators without a denominator. Unit costs can help describe to your stakeholders, yourselves, what you're buying in terms of the outputs of the system, in terms of the things you care about. For example, the infra costs required to sustain 1 million requests per minute. Over a very long term, as I said at the start, the economies of scale of systems matter. If you're lucky enough to keep growing, you need to get better economies of scale as you grow, otherwise you will eventually fail. And you need a way to understand that and measure it, and unit cost is a better framework for thinking about that and describing that. Can we set expectations for these in terms of the SLIs and SLOs? Right. This is all about an attempt to connect cost with value, rather than just obsessing about the cost of stuff. Your infrastructure bill, your cloud bill doesn't self-describe what it's for, who's using it, what value it's driving, or what parts of it are driving what value. Being able to measure your systems and describe the economies of your systems in unit costs helps you to do that. And the whole cost versus value thing is where I want to end this, actually, because lowering costs is not the goal. Saving money is very easy. Just turn the computers off and delete all the data. Job done, right? But that's not going to probably not be a good, successful outcome for your business or your customers, right? The cloud bill, the infrastructure bill doesn't exist in a vacuum. Yeah. By all means, go and pick the low-hanging fruit. If you wait long enough, it will accumulate. It's that sawtooth effect again. And then by all means, go and look to optimize your systems because that's a good thing to do, but understand the trade-offs, the whole Chesterton's fence thing. Why is that resource there? Is that failover capacity for that service or burst capacity for that service or an experiment? Understand what you're cutting first. I would posit perhaps that maximizing value is closer to what the goal is here. I don't think that's quite precise enough. If anyone can articulate this better, then please, I'd love to hear about it. But it's about we need to bring in the other side of that equation from cost, right? What are we buying with all this money? Is that valuable to the objectives of our business? Is it valuable to our customers? And it's not arithmetic, some of it. You can express it in terms of, 1 million requests per minute or checkouts or 1 million search results or whatever it is. But, what's 30 minutes of faster recovery worth to your customer happiness? What's 12 months of retention worth for that data set to some compliance objective or whatever? What business objectives are we trying to support? What value are we trying to drive? It's like a good SLO, really. We want to connect the cost. We want to describe the value of what we're getting for that spend in terms of value we're delivering to our users and our customers. And that means engaging with your leaders, your stakeholders, your customers to figure that out so you can describe it, measure it and describe it in a way that those stakeholders and customers can understand. So that's what good might look like. No surprises. I'm trying to connect as much of the spend as possible to the value it delivers to your customers and your users. I work with some very clever people at Shopify. I'm here today representing their efforts, so thank you very much to them, and thank you for listening to me today. Thank you.